We've discussed classical mechanics, Newton's laws, conservation of energy, conservation of momentum. All of that is on firm physical footing. We've got pretty good understanding of that. We've discussed electricity and magnetism. So we know how charges repel each other. We know how moving charges are affected by magnetic and electric fields. So all of that is taken care of. And historically, that puts us around about 1900. And at the time, physicists were thinking that between classical mechanics and electricity and magnetism, we understand pretty much everything there is in the universe. But there's some trouble brewing. There's a couple of things that don't quite fit in with the standard theory. And at the time, physicists were mostly thinking these are just a couple of hurdles we got to get around, but we can just patch it up and everything will still be governed by classical mechanics and electricity and magnetism. Two of the problems that were popping up around 1900, one of which was the speed of light. I made reference to this last time. The theory suggests that the speed of light should be a constant. And on the surface, that doesn't seem too implausible. So the speed of light is constant. If the speed happens to be 50 miles an hour, I turn my flashlight on, the light comes out at 50 miles an hour. It's a lot faster than that, but let's stick with the 50 mile an hour example for now. So you turn your flashlight on, it's 50 miles an hour, light comes out at that speed. The problem is, what happens if you're driving? Right? If you're driving at 50 miles an hour, so we're driving down the street, and you turn your headlights on, well, if the speed of light is 50 miles an hour, and you're driving at 50 miles an hour, the light's not going to go anywhere. So how do we account for this? In fact, how do we account for the fact that if you're driving at 50 miles an hour, and the light is supposed to move at 50 miles an hour, relative to you it might be moving 50 miles an hour, but for somebody sitting on the side of the road, he would see the light moving at 100 miles an hour. So there seems to be some contradiction there. Okay? That is the topic of a subject called relativity. We're going to save that for another time. Okay? So that's the speed of light. The other main problem around 1900 was the structure of atoms. So at this point, scientists, or at least most scientists, believe that there are atoms, and people started to examine the properties of atoms in the context of classical mechanics and electricity and magnetism. And as we'll see, there are some problems that start to show up when we start to analyze this in the context of classical mechanics and electricity and magnetism, because it turns out that's not the only physics that's there. In 1900, just a few years later, physicists were about to see a huge explosion in the amount of knowledge we have about atoms, not just atoms, but the universe as a whole, how time and space really work. Let's discuss some of the experiments that allowed people to figure out some of the structure of atoms and materials. So we've already talked a bit about cathode rays. Cathode rays are the little green lines of light that you saw that arised from electrons that were being shot out of the metal. We use them in TVs and oscilloscopes, and they're very practical. But it's basically just you're shooting out electrons. Now, let's suppose that I set up an instrument that looks like this, and in this instrument, we put some positive charge on a top plate and some negative charge on the bottom plate. Just have a parallel plate capacitor. So I have electric field pointing down. But we also include some magnetic field that is perpendicular to that electric field. And we're going to shoot some electrons into that plate. Now, when the electron goes into the plate, it's negatively charged, so it's going to feel an electric force up. And if I do my right-hand rule, since my electron is moving to the right, it'll be V cross B, so I should have a force up, but it's negative, so it'll flip it down. So we have two forces that are counteracting each other. And if I tune those forces exactly to be exactly the same magnitude, the electron beam should just go straight through my plates here. My electron beam should go straight. Now to do that, we have two forces. We have an electric force and a magnetic force. So I have my electric force, QE, and my magnetic force, QVB. And the total force, they're in opposite directions, so I'll put a minus sign on the magnetic force. And the total force should equal 0 because the electrons are not accelerating up or down. So this gives me a way to select my velocity. Sometimes you call this a velocity selector. The q's will cancel. And then the velocity that's left over will just be the electric field minus the magnetic field. So any electrons that have this velocity will pass right through, straight. Anything that doesn't have that velocity will feel the force up, so it'll get brought into the top plate or down, depending on whether it's going too fast or too slow. If the velocity is faster, the magnetic force will be bigger. If the velocity is slower, the magnetic force will be smaller, so the electric force wins out. But only electrons that have just the right speed are going to pass through. So we can select what the velocity is. We know what the velocity is because we can choose it by picking the electric and magnetic fields. Okay? So this part is sometimes called a velocity selector. The next part, so now we enter this chamber of our device, and it still has a magnetic field pointing in, but it does not have an electric field. So as the electron comes in, it's moving in this direction, and it feels a magnetic field, which means it's going to feel a magnetic force. So the force is going to be V cross B, which means the force would have pointed up. But since it's a negative charge, that force is going to point down. And it's going to have its path changed. So it's going to start to curve around like this. And at every point, if you do V cross B, you'll see that it's always pointing in, which means we're going to get some sort of circular motion. So velocity is this way. But this is just going to be circular motion with some radius, and we can measure what that radius is. So we're just going to call this some radius r. Now, for this second segment, we get a different net force. Because there is no electric field, there's just a magnetic field. So the electric force, or the total force, will just be the magnetic force, which is Q times V times B. We already know what the velocity is because we selected that in our velocity selector. And we clearly have an acceleration here because we're undergoing circular motion, so our acceleration is always toward the center, which means our net force should be a centripetal force. The centripetal force is the mass times the centripetal acceleration. So that's the mass times the velocity squared over r. Well, we can measure that radius. That's easy enough to measure. We can measure the velocity. In fact, we've selected the velocity by choosing the electric and magnetic fields. So let's see what's going to happen here. One of my v's is going to cancel. And then what we can solve for is the charge over the mass. I'm going to move the mass over to the other side. So we're going to be left with, let's see, that's going to be a v up top over r. And then I have to move a b over to the bottom here. So this gives us a way to find out the ratio between the charge and the mass of an electron. So since these are electrons, I'm going to put QE and ME over there. So I can find the charge to mass ratio. Now, that is not as good as finding the charge and the mass separately. It turns out it's very difficult to separate these two out. And at the time, the best that physicists could do is find the ratio of the charge to the mass. Okay? So we can't find the mass of an electron. We can't find the charge of an electron, not yet anyway, not historically. But by choosing the velocity, measuring the radius, and measuring the magnetic field that we put into that region, we can at least find something. We can find the ratio of the charge to the mass. Now, this device, many of you have seen it before, since many of you have had chemistry. This is called a mass spectrometer. And you use this to measure the mass of different known ions. So if you know that an ion is going to have a charge of +1 or +2, you can figure out what the mass is, because if you know the charge, you know everything in this equation but the mass. But for cathode rays at the moment, we can only figure out what the ratio of charge to mass is. How do we figure out what the individual charge and individual mass of an electron is? It wasn't until some years later that someone came up with a brilliant idea for how to measure the charge and mass of an electron separately. And that man's name was Robert Millikan, and he did a series of experiments between about 1908 and 1913. And what his idea was he said, all right, I'm going to take a parallel plate capacitor, top plate, bottom plate, we're going to apply a voltage across, and we're going to spray some oil in between those plates. So they took essentially a perfume bottle, old-timey perfume bottle, and sprayed this mist of oil into the plates. And you're going to have some oil droplets that are passing through the plates. Now, occasionally, those oil droplets will pick up or lose an extra electron, or maybe a couple of electrons. Most of them are just going to fall to the ground due to gravity. But every once in a while, one will pick up or lose an electron, so it will have a net charge. And if it does pick up a net charge, there will be an additional force on it. So we know the force of gravity is pulling the electron or the oil droplet to the ground. However, if it picks up an extra electron, it will feel a net force up. Now, we can figure out the mass of the oil droplet by looking at the time it takes for the oil droplet to fall to the ground. I'm not going to go into the math of that here, but if you look at the terminal velocity of the oil droplet, you can use that to figure out its radius, and then you can use the density of the oil to figure out the mass of that oil droplet. But the electric force depends on, as we know, charges create fields. Here's your charges creating the electric field between the plates. And there's a charge on the oil droplet that's some multiple of the number of electrons. So it's going to be the charge times E, but that's going to be equal to some number of extra electrons. Maybe it's 1 extra electron, maybe it's 5 extra electrons. So the number of electrons times the charge of an electron times the electric field, which is given by the voltage divided by the distance between the plates. Distance between the plates, we're just going to call that D. Okay? So I can measure the voltage that it takes to levitate that oil droplet. I can measure the distance between the plates. That's a constant. Millikan actually set this up so that you could vary the voltage continuously. So you know if the voltage is not quite right, you can tune it so that the droplet just levels out. And then we can use this to measure the charge, because we know everything here. We know this. We know the forces have to be equal to each other. The electric force has to equal the force of gravity, which will mean that the charge of an electron times the number of electrons times the voltage over the distance, all things I can measure except for these things, that has to equal mg. Now, I should point out some historical facts here. So at the time, people didn't know that electrons were particles. All they saw was some green flashy light, and they kind of thought that maybe it might be fluid. Some green ooze that's coming out of the metal. Some people thought they were particles, some people did not think that they were particles. But the Millikan oil drop showed pretty definitively that these had to be particles that were coming out. The reason being is that Millikan, from this, he could measure the charge on each oil droplet. And so what he did is he made a histogram of the number of counts he got for different charges. These are going to be in units of 10 to the minus 19 coulombs. And what Millikan found was that he never got anything that was 1 times 10 to the minus 19 coulombs. He only got things that were 1.6 times 10 to the minus 19 coulombs. And then he never got anything that was 1.7 or 1.8 or 1.9. The next number he got was 3.2. And then he got some oil droplets that had a charge of 4.8. And he built up this histogram. And the histogram looked like this, with humps that have even spacing. The interpretation of this is that that green beam that's coming out of the cathode ray, which has a negative charge, that cannot be just some green ooze. It has to be individual particles of electrons that are very, very tiny. We know that there have to be individual particles because if I interpret this the right way, this oil droplet has 1 electron on it. 1 electron with a charge 1.6 times 10 to the minus 19 coulombs. If you have 2 electrons on it, we double that. So you get 3.2 times 10 to the minus 19 coulombs. If you have 3 electrons on the droplet, you get 4.8. You have 4 electrons on the droplet, you get 6.4. So there's a few peaks out here, a few more peaks out here. One's going to be at 6.4. But the spacing of the peaks is always the same. So that tells us the charge has to be, the word they used was quantized. It only comes in certain bundles. You can only get a 1.6, I can't get a 2.0. I can get a 1.6, a 3.2. We get certain bundles of charge that are allowable, and other bundles are not allowed. So the word they use is that the charge is quantized. Quantized, or quantum, just means bundles of charge. They come in discrete packets, as opposed to continuous packets. You know, I can have anything from 1.6 to 3.2 if it's continuous. Here, you can't get anything from 1.6 to 3.2. You just get 1.6 and 3.2 with nothing in between. So Millikan had this genius experiment, and it not only figured out that the charge, that electrons were particles, it figured out their charge and also their mass. So from that data, we can predict the charge of an electron is 1.6 times 10 to the minus 19 coulombs. And Millikan was no dummy. He was a big, he read a lot of the papers of the time, so he knew that people had already figured out the charge to mass ratio. Once you know the charge to mass ratio, and you figured out the charge, then you also know the mass of an electron. And so they were able to figure out the mass of an electron, and they figured out that electrons are really, really tiny. They had a mass of 9.11 times 10 to the minus 31 kilograms. Okay, so this is one of the first fundamental particles that scientists had discovered. And they were able to measure pretty accurately their charge, the charge and its mass, even though it's so tiny. Now, you could never weigh this on a scale, but if you have a little bit of ingenuity, you can figure out how to measure the mass of very, very tiny things. So, Millikan discovers that electrons are particles. Not only are they particles, but they're very, very tiny particles. 10 to the minus 31 kilograms. Now, not only is that small, that's even small for atomic masses. So the picture that they had at the time had to depend on the fact that electrons were very, very tiny. They made up a very small percentage of the mass that made up matter. But you need an equal amount of positive and negative charges. So how do you have an equal amount of positive and negative charges if the negative charged objects are so tiny? Well, the model they came up with, they called it the Plum pudding model, which is basically, you have a soup of electrons, teeny tiny little electrons, and those electrons are swimming around in a sea of positive charge. And the reason they called it the plum pudding model is because you can imagine the electrons are little raisins swimming around in a big soup of plum pudding. I've never had plum pudding. I assume it's, actually, it'd have to be plums. All right, so your electrons are plums swimming around in your plum pudding. But they're just kind of floating around there, while most of the mass of the soup has to deal with these, the soupy layer of the positive charges that are surrounding them. And Rutherford, Ernest Rutherford, decided to do an experiment to test this. So he was working a lot with radioactive particles. In particular, he was working with alpha particles. And alpha particles are quite a bit larger, on the order of 1,000 times larger than the electrons. So what he did is he had some radioactive source of alpha particles. So some alpha particle source over here, which is basically some radioactive material that's just emitting alpha particles. And let me get my mask a little bit more correct here. He essentially, got to make my electrons tiny since they're pretty tiny. He essentially fired those alpha particles towards some matter. In this case, he took a very, very thin sheet of gold and fired the alpha particles towards them. So our alpha particle source is going to be emitting alpha particles. Let me just draw the alpha particles rather than the source. Here's some big bulky alpha particle coming in. And you would expect that since the alpha particle is several thousand times larger than the electron, several thousand times more massive, that for the most part it's just going to go right through. The electrons are not going to interfere with it. And if an electron gets in the way, it's just going to get knocked out of the way. It's several thousand times smaller. It's like hitting, driving a Mack truck through a street with some baseballs in it. The baseballs aren't really going to do anything to stop the Mack truck. The issue came up, and that was true most of the time. 99% of the time, alpha particle went straight through. That 1% of the time, though, something weird happened. And the alpha particle bounced back. Right? That's weird. That's like, you're driving your Mack truck down the street, and there's a bunch of baseballs there, and then occasionally the Mack truck hits a baseball, and it goes flying backwards in the other direction. Or you're dropping bowling balls into a pool, and then occasionally, every once in a while, the bowling ball hits the surface of the pool, comes back out, and hits you in the face. Very hard to understand what's going on there, given the plum pudding model. However, what Rutherford was smart enough to deduce was that the plum pudding model wasn't quite the right picture. Because the only way an alpha particle would bounce back 1% of the time is if you had a very massive particle somewhere in the material. And that very massive particle had to be very small spatially. So even though it had a lot of mass, it had to be very tiny, so it had to be very, very dense. And so the actual picture of what was going on, as I mentioned before, this was a gold foil film. The actual picture is that you did have these tiny electrons, but you had these very heavy, dense nuclei. And for the most part, let me again readjust my scale here. Here's your alpha particle. Alpha particle is about the same size as the nuclei. And most of the time, since the alpha particle, or since the nuclei were so very small, since they were both so small, the alpha particle went through without hitting anything. So even though there's tons and tons of nuclei here, they're so tiny, most of the time the alpha particle just goes straight through. Right? It's not like it's Plinko. It's not like it's going anywhere. Ding, 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 ding. No, it just goes straight through. But if it does go on a course where it comes close to the nuclei, it's going to bounce back, almost straight back. Because that nuclei, even though the alpha particle is thousands of times bigger than the electron, the nuclei is still many times bigger than the alpha particle. So by measuring the angle that the alpha particle gets deflected by, Rutherford was able to determine the size of the nucleus, and he was able to, in fact, to determine that there was a nucleus. So this experiment, this Rutherford scattering, we call it Rutherford scattering because he looked at how the alpha particles scattered off of the gold foil, was able to determine that atoms have very positively, or very dense, positively charged nuclei. So Millikan discovered that electrons were particles with a mass and a charge that he could determine from his oil drop experiment. Rutherford discovered that atoms do not have this soupy positive charge that goes everywhere. It's actually a very dense positive charge that you can tell because if you slam alpha particles into it, they bounce back. This led to what should be a very clear picture of the atomic structure. And that atomic structure was kind of influenced by the theories at the time. So one of the main, very successful theories was Newton's theory of gravity, which said that there's a sun and there's an earth. There's a gravitational attraction between them. The sun's very large, so it doesn't get pulled with quite the same acceleration as the earth, but the earth basically gets pulled toward the sun. Well, now we have the same picture that we can apply with electrons. And in fact, the electrical force looks very similar to the gravitational force. You've got some positively charged nucleus. You've got some negatively charged electron that's going around the nucleus. There's an electric force pulling the electron toward the nucleus. The nucleus is much more massive, so it does not have as great of an acceleration. The electron goes around the nucleus in circular motion. There's one problem with that. The electrons are going around the nucleus in circular motion. By definition, circular motion has an acceleration. What happens when you accelerate a charged particle? Well, we said before that electromagnetic radiation arises when you start shaking a charge. You shake the charge, that jiggles the electric field, that releases electromagnetic radiation. Why is that a problem? Well, that energy is going off. It's gone. The electron would start to lose energy because it's emitting electromagnetic waves. And as it loses energy, it's going to lose speed. So as it loses speed, what's going to happen is it's going to start to spiral into the nucleus and crash into the proton, destroying all life as we know it. And this happens very, very quickly. So for some reason, the electron doesn't do this. Okay? How could this be? We know accelerated charges emit electromagnetic radiation. We know these are charged particles. We know there's a dense center and an electron that's a lot tinier. We know the electric force law between those two should just be the same, should act the same way as the gravitational force law. What could possibly be different? What's going on in this situation? One of the problems that came across in early 20th century physics was known as blackbody radiation. So we've talked previously about black bodies, so that if you heat up a dark object like a piece of iron, you know eventually that object is going to start to glow. Initially it'll start to glow red, it'll be red hot, then as you heat it more and more it becomes white hot. So why do we get those colors out as you increase the temperature of the object? Why is it that when you heat something up you get particular colors? Well, that's the subject behind blackbody radiation. And in 1900, this was a very confusing topic for physicists. So they don't know, they have an idea that there are atoms at the moment, but they have no idea why atoms should start emitting light as you start to heat them up. So like any good physicist, they tried to come up with a model to predict what was going on inside the matter that you were heating up and why it was producing light. And the basic idea was light is a form of energy. So as you excite an object by heating it up, as you give it more thermal energy, some of that energy transitions to light waves. So it forms electromagnetic radiation. So you can imagine that you have this black box, and inside the black box, you start to get light waves of different wavelengths. So depending on the size of the box, you might get some wavelengths like this, some wavelengths like that, etc., etc. And occasionally, every once in a while, you can imagine that this is kind of like a box that's a cavity. Cavity just means hole. But occasionally, some of the light will escape out of the box through some hole. You can use that when the light comes out. You can see what color it is, and you can measure how much of each color comes out. So physicists made a model of this, and they predicted what intensity of light you should get for each different wavelengths by assuming that this was just some object that was in thermal equilibrium. So that each wavelength of light got a certain amount of energy. And lo and behold, if you plot the intensity of the light as a function of the wavelength lambda, the model predicted you get a curve that looks like this. So for large wavelengths, you get fewer and fewer, or smaller and smaller intensity of light, I should say. So somewhere out over here, we have the infrared wavelengths. Somewhere over here, we have the ultraviolet wavelengths. Large wavelength is more on the infrared scale. Small wavelength gives you more into the UV gamma ray scale. And we get a plot that looks like this. Now, if you look at that plot for just a little bit, you can see why that's a problem. See it yet? Give it a minute. Why would, all right, so if this were true, why would that be bad? Well, part of the problem is right here. It blows up to infinity around the UV. If this were true, then as you heat an object up, in fact, for any finite temperature, you get an infinite intensity of light for short wavelengths. If this were true, we would all be burned to a crisp, because every object that wasn't at absolute zero temperature would have an infinite amount of low wavelength light. So it would be tons and tons of UV rays and gamma rays smashing into you and burning you to a crisp. So for this reason, this model had what they referred to jokingly as the UV catastrophe. Now, I think that's catastrophe. I think it has an H in it. Now, it wasn't so much of an actual catastrophe, right? We knew we weren't getting burned to a crisp. So we knew something had to be wrong with this model. And in fact, the model was pretty good. It worked very well for large wavelengths. So it would work well for a time, and then there was a deviation between what we actually measured. So this yellow line is going to be the actual experiment. There was a deviation between what the experiment was giving you and what the model predicted. Okay. So how do we amend that? Well, there was a gentleman named Plum who had a pretty good answer for how to fix it. He made basically the same calculation, but he assumed that there was a minimum amount of energy you could get out of the light. There was a minimum amount of energy that you could get out of light of a certain wavelength or frequency. The minimum energy, so basically he was counting the amount of light you got out at each different wavelength or frequency. Minimum energy, he said, was going to be this. In fact, he said it wasn't just a minimum energy. Energy came in multiples of h times f. That's the energy of light. This is the frequency of the light. This is a constant. It has come to be known as Planck's constant since he's the one who came up with it. It's equal to 6.63 times 10 to the minus 34 joule seconds. And lo and behold, if you make the assumption that the energy of light comes in multiples of h times f, you get exactly the experimental curve that people had already measured. Now, at the time, this was kind of a fudge factor. Planck discovered that if you do this, you get the right results. So let's just do this because it makes the right predictions. However, this turned out to be a much deeper interpretation of what was going on here. Another experiment that was difficult to explain at the time, this is about 1905, was something called the photoelectric effect. And it is called the photoelectric effect because you take a photo, which I believe is the Greek word for light, and you shine some light on the metal. So that's the photo part. The electric part is that when you shine that light on the metal, occasionally you have electrons popping off. These electrons leave with some kinetic energy. Fairly simple. We send some energy in, it pops some electrons off. But there were a couple of subtleties involved in this experiment that were very important. Subtlety number one. You couldn't do this with just any old light. It had to be light above a certain frequency. So you need a frequency of light above some threshold to get current. So in this case, it's not current through a wire, it's current, still current though, because we have electric charges that are moving. So that's one thing. You couldn't, if I did this with low frequency light, so like radio waves, for some metals, the electrons wouldn't come popping off. But for that same metal, if I were to do it with a higher frequency light, like purple light, then the electrons would come popping off, depending on your frequency. That was subtlety number one. Subtlety number two, a higher intensity didn't necessarily get you, didn't really help you out. So even if I took radio waves with a very high intensity, so really intense radio waves, or let's say red light, really intense red light, the electrons might still not come popping off if they weren't above that threshold frequency. But if you were above that threshold frequency and you added a higher intensity light. So you went from dim red light to bright red light. If that frequency was above the threshold, then you'd get more electrons coming off. Right? They'd come off at a faster rate. So higher intensity light, higher intensity again is just brighter. Higher intensity gave you more electrons coming off. But you could measure the kinetic energy of the electrons, and they all came off with the same energy, even though you were putting more energy in. More electrons come off, or come out, I'll say, but with the same energy. So the energy depended on, the energy that the electrons left with depended on the frequency of the light. It did not depend on how much energy the light came in with. It didn't depend on the intensity of the light. Now that's a little screwy, but we want to put ourselves in the context of people in the 1900s. And it turns out if you think about this experiment, the way people in the 1900s were thinking about, early 1900s, so pre-1905, I guess 1800s. This experiment is very, very screwy. So let's, to explain how screwy this is, I'm going to give you guys a little bit of an analogy here. So let's, instead of talking about light and metals, which are a little less familiar, let's talk about pool parties. So our pool party analogy here is going to work like this. It's the end of the year. All of you guys have passed, or at least most of you have. So we're throwing a giant pool party because, yay, everybody passed the course. And here's our pool party. In fact, it's not even a pool party. We'll go out to the beach. Here's the dock on the beach. Here's a couple of you guys smiling because you got good grades in the course. Drinking some non-alcoholic beverage, because I can't get away with alcoholic beverages. Giving those to you guys would be really bad. And it's a big celebration and a party. However, here's the water. I have one more surprise for you guys, since you know I love to torture you. In fact, here's me out in my boat. There's me, there's my bifurcated tail. And I have with me a wave machine. Here's my wave machine. And my wave machine can make waves of any type. I'm going to send a giant tsunami wave at you. Giant tsunami wave. So what's going to happen is this. Send this huge tsunami wave. The peaks of the wave are enormous. They're the size of the Empire State Building. And here comes my wave, going over you guys, and nothing happens to you. You just smile there, with that stupid smile on your face. Nothing happens. You don't get knocked off the dock. You just stay right there. But, if I repeat this experiment, and instead of setting my wave to have a high amplitude, I don't care about the amplitude so much. I'm just going to make the frequency really, really high. So instead, I take my wave and I give it a really high frequency. In fact, I don't even need my wave machine. I can just go like this in the water really, really fast and send out really, really short wavelength wave. High frequency, low wavelength. If I do that, then what happens is you guys go flying off the dock, spilling your non-alcoholic beverages, looking sad and confused. That's the analogy. To Now that doesn't seem to make much sense if we're talking about pool parties. But in the analogy for what's happening to physicists in 1900, that's what's going on in metals when you shine light on them. We send a wave in. If it's got a huge amplitude, doesn't make a difference. You're not going to knock any electrons off if the frequency isn't big enough. If the frequency is big enough, we are going to knock electrons off. In this analogy, you guys are my electrons. And if I make that frequency even bigger, you guys are going to come off with more kinetic energy. So you guys leave with some kinetic energy. If I make the amplitude bigger, you guys are going to get knocked off even faster. With the same kinetic energy, but more of you are going to get knocked off. So you're knocked off at a faster rate, even though each of you individually gets knocked off with the same kinetic energy. That's very confusing if you're thinking about it in 1900 terms. But fortunately, there was a very bright man named Albert Einstein who came up with an explanation for why frequency will change the amount of energy you get knocked off with, even though frequency doesn't seem to have a whole lot to do with kinetic energy. And he also explained why higher intensity knocks off more electrons more frequently. And Einstein's interpretation actually built off of the work that Planck had done with blackbody radiation. So Einstein's interpretation was this. This is that Einstein. He had a really good year in 1905. Really good year. One thing is he figured out this thing. And the interpretation is that light has particle properties. Not just wave properties. So particle properties in addition to the wave properties it already had. So that's one thing Einstein did. He also did a few more things. Figured out that, found a way to prove that there was molecules, and discovered that space is not the way we thought of it before. It's actually combined with time, and that you can bend space and time. That's a topic for another day. For now, we're just concerned with the idea that light has particle properties. That's a confusing thing, right? We're used to thinking about light as a wave that can interfere with itself. Now we're saying it's got particle properties. And part of having particle properties is that when you use energy, when you use light to pass off energy, that energy comes in lumps. Here's what I mean by the energy comes in lumps. You've got to remember, we're shining light on it, and we're going to shine light of two different wavelengths, two different frequencies. Long wavelength and a short wavelength. What Einstein's interpretation says is that light has these particle properties, and that the long wavelength light, it's kind of like it has very low energy particles. Almost like, you can imagine they're like very tiny particles, not a lot of energy in them. That's for the long wavelength light. For the short wavelength light, short wavelength has a long frequency. I'll remind you that if this is the speed of light, or any wave speed, the wavelength is just inversely related to the frequency. So the high frequency light has a low wavelength. But this light, if we're thinking about the light in terms of particles, it has very energetic particles. You can imagine them as big bowling balls of energy coming in, and those bowling balls come in and they knock the electrons off. But the teeny tiny little pebbles of light, that's not enough to knock an electron off. So going back to our pool party analogy, if you guys are standing on a dock and I throw a bowling ball at you, that's going to have enough energy to knock you off. But it doesn't matter how many little tiny pebbles of sand I throw at you. It might be annoying, but I'm never going to be able to knock you off. Doesn't matter how many of them I throw. And that's the interpretation that makes sense for this photoelectric effect. Intensity of light, how bright it is, just tells you how many of these particles you have. So if you have a very intense, very bright light, very bright red light, that's like having a bunch of teeny tiny little particles, a bunch of these sand particles coming toward you. None of the sand particles individually has enough energy to knock you off, but you might have a lot of energy in total because there's lots of sand particles coming at you. In contrast, if we look at purple light, which has a lower wavelength, a higher frequency, it's like I'm throwing giant bowling balls at you. And even if I don't throw very many bowling balls at you, each individual bowling ball has enough energy to knock you off the dock. And in this case, has enough energy to knock the electron off of the metal. If I increase the intensity of the purple light, all I'm doing is adding more bowling balls so that the energy that you get knocked, or the number of electrons that gets knocked off increases so that it happens at a faster rate. But if I look back and forth between the red light and the purple light is only going to be the only one that has enough energy to knock you off. And the bigger I make my particles, so if I go from little sand pebbles to bowling balls to let's say I start throwing car-sized boulders at you. If the car-sized boulder hits you, you're going to come off with more energy. So it's really the frequency of light that determines the energy that the electrons leave the metal with. If you have a big frequency, that's a lot of, each individual particle has a lot of energy, so the electron's going to get hit with a lot of energy all at once. That's what I mean by the energy comes in lumps. You get one big bowling ball at a time, that's your lump of energy. If you have a long wavelength, small frequency light, you don't have as much energy per particle, so you don't get hit with enough energy in that lump to knock an individual electron out. Now, we can interpret this more mathematically, or we can write down some equations that we can use to make some quantitative predictions. Because the energy of the light has to go somewhere. And here's where Einstein borrowed the idea from Planck, because Planck had basically said there's some minimum energy that my light can have. The same thing is true here. There's some minimum energy my particle of light can have. It's just the energy of a particle of light with that particular frequency. So in this case, it's the exact same formula Planck used and the exact same constant. So this is the energy of the light. And that's a little, atomic physics is a little confusing. But even though it's confusing, energy still has to be conserved. So that energy has to go somewhere. So where does the energy of the light go if it gets absorbed by the electron? Well, it goes to two places. The first place it goes is something I will represent by the Greek letter phi. Phi is called the work function. And we can think of this as the binding energy of the electron. So it takes a certain amount of energy just to remove the electron in the first place. The electron's inside its metal atom. There's an attraction between it and the nucleus. And just to get that electron out, you've got to give enough energy so that you can overcome that attractive energy. So this work function tells you how much energy it's going to take to pull an atom out of your piece of silicon or gold or whatever the metal happens to be. So it'll be different for different metals. That's the amount of energy it takes to pull an electron out of a given piece of metal. Any extra energy just goes into the electron as kinetic energy. So that's your kinetic energy of the electron. That's the energy that it leaves with. So we can see by this formula, if the if the frequency is higher, well, it doesn't take any more energy to remove an electron. Once you have enough energy, the electron can come popping out. But if you add more frequency, you've got a bigger bowling ball, boulder of a photon that's coming in. By the way, I should mention, each of these little particles of light are called photons. Just like electrons are particles of electricity, photons are particles of light, photons. The Greek word for light is photon, I believe. This is the energy of a single particle of light. That energy goes into partly pulling the electron out in the first place, and any energy that's left over goes into the kinetic energy of the electron.